The fundamental purpose of any electronic amplifier is straightforward. Take a weak input energy signal and magnify it without losing its original shape. But if you place two transistor amplifiers side by side, built with the exact same physical components and circuit topologies, they can behave in completely contradictory ways. One configuration perfectly reproduces the incoming signal. The other chops the signal in half. In standard engineering terminology, these distinct operational behaviors define Class A and Class B amplification. Identifying these classes typically leads students to search for different wiring patterns on a schematic. However, the schematic diagram does not contain the answer. Classification is determined entirely by a hidden two-dimensional geometric boundary condition operating inside the transistor itself. We call this boundary condition the DC load line. By deriving this load line from scratch, the physical limits of amplification emerge as a direct result of the circuit's geometry. Understanding amplifier class requires mapping the mathematical boundaries of the transistor's possible energy states rather than analyzing the physical copper wiring. This coordinate system maps a transistor's operation, with collector current on the y-axis and collector-emitter voltage on the x-axis. A transistor cannot output infinite current or voltage. It is strictly caged by the circuit's power supply and its load resistor. This creates our first absolute boundary on the x-axis, known as cutoff. At cutoff, the collector current drops to zero. Because no current flows, the full supply voltage, VCC, drops across the transistor. On the opposite end, we find the second absolute boundary on the y-axis, saturation. At saturation, the voltage drops to zero, and the maximum current is determined strictly by dividing the supply voltage by the load resistor. Connecting these two absolute extremes creates a definitive geometric boundary. This diagonal connection is the DC load line. The transistor's internal state remains fixed to this diagonal path, which dictates the possible range of every current and voltage swing. The DC load line acts as a physical rail for the transistor, establishing the hard boundaries of the circuit's performance. Before a signal is introduced, the transistor sits at a resting position called the operating point, or Q point. An engineer can choose to place this Q point in the exact mathematical center of the DC load line. This central placement gives the transistor the maximum possible room to fluctuate in both directions. When we apply an AC input signal, like an audio pulse, the transistor begins to fluctuate around this center. The positive half of the input signal pushes the operating state up the load line, increasing current toward the saturation point. The negative half of the signal pulls the operating state down the load line, decreasing current toward the cutoff point. Because the Q point started in the center, neither the upward nor the downward swing hits the extreme ends of the load line. This specific operational dynamic defines Class A amplification. In a Class A setup, the transistor never shuts off, conducting for the entire 360 degrees of the input signal cycle. A centered Q point creates a perfect unclipped replica of the input signal, which is the primary hallmark of a Class A amplifier. What happens to the output if we slide the resting state away from the center? We can relocate the Q point down the load line until it rests exactly on the cutoff boundary, where resting current is zero. We apply the exact same AC sine wave used in the Class A example. The positive half of the input signal pushes the Q point up into the active region of the load line, producing a clean output curve. Then, the negative half of the input signal attempts to pull the Q point further down, below the x-axis. The transistor cannot produce negative current, so the operating point simply flatlines against the cutoff boundary. In the final output waveform, the entire negative half-cycle has been physically erased. This half-cycle conduction dynamic, where the transistor only operates for 180 degrees, defines Class B amplification. Moving the Q point to the cutoff boundary converts the amplifier from a full-wave reproducer into a half-wave rectifier through geometric positioning alone. Side by side, we see the full-wave output of Class A contrasting with the chopped half-wave output of Class B. Both result from identical input signals on the same load line. Classification is dictated purely by the resting Q point's coordinates. Resting in the center means the transistor is always drawing current, which provides high signal fidelity at the cost of poor energy efficiency. Conversely, resting at cutoff means the transistor draws zero idle current, which maximizes efficiency but sacrifices half the signal data. Engineers select an amplifier class to balance the trade-off between signal purity and power consumption. By mastering the mathematics of the DC load line, you gain precise control over the fundamental limits of analog electronics.